Good morning, CP Pre-Calc. What we're doing is another day, just another day of solving trig equations. All right, guys, another day of solving trig equations. And what we're going to do is do something a little different today. We're going to use identities to solve trig equations. That's what we're going to do today. So let's take a look at some of these identities. We already know a bunch of identities, but I'm going to give you a couple new identities. So we have a couple new trig identities. So make sure we copy these down. So a couple new trig identities. So the new trig identities we're going to look at today is they're called double angle. And we're only going to worry about the cosine and sine for the double angle. But it is a little different because cosine has 3 double angle identities. Sine only has 1. So let me start with sine. The sine double angle identity says the sine of 2 theta. Double angles, pretty simple. 2 times our angle measurement of theta will be equivalent to 2 sine theta cosine theta. All right, another double angle. We have cosine. Cosine of 2 theta. We multiply our theta by 2. That's the same as cosine squared theta minus sine squared theta. Okay, now I said there's multiple. There's 3 cosine double angle identities. 2 cosine theta is also equivalent to 2 cosine squared theta minus 1. And cosine 2 theta is also equivalent to 1 minus 2 sine squared theta. So these are our 4 new identities that we're going to be working with, plus the original identities that we already know, which are Pythagorean identities, are reciprocal identities. We can still use those, but these are 4 new ones we're also going to work with. So we're going to start with, again, our same directions. Solve the trig equation on the interval 0, 0, which should have the bracket there. Sorry, guys. 0 to 2 pi. All right, guys? We're solving on that same interval, so I didn't change anything there. So the first problem we're going to look at, we have cosine of 2 theta is equivalent to cosine theta. Now, what I want to emphasize here, guys, is I need to use my double angle to get rid of anything that has a 2 theta inside the cosine function. So right here, I have cosine of 2 theta. Now, our goal is really going to be to try to write everything in terms of the same trig function so that we're able to solve it. So if I see this as cosine of 2 theta, and I want to plug something in so I get rid of that 2 theta here, I'm going to try to keep it in terms of cosine. So by doing that, I look up here at my cosine double angles. This one has cosine and sine, and this one is sine squared. The middle one has just cosine. So I'm going to plug that one in because that allows me to keep my equation just in terms of cosine. So instead of cosine 2 theta, I'm going to substitute this value of 2 cosine squared theta minus 1 in. And that's equivalent to cosine theta. Now I have everything with just a cosine theta. I don't have that double angle anymore. Now, so once I get here, I'm going to solve it, just like we've been doing the past couple days. Now, I'm going to identify this as a quadratic because it's squared. So I'm going to bring everything to the left. So you're going to have 2 cosine squared theta, move the cosine, minus cosine theta, minus 1 equals 0. And this one happens to be factorable. So let's see, we take the 2, multiply it by the negative 1, I get a negative 2. And then I ask myself what multiplies to negative 2 and adds to 1. And we know it's negative 2 and 1. So I can now break that up, my middle 2 terms up into negative 2 cosine theta and negative 1 cosine theta. We break that up. Oh, plus 1 cosine theta, sorry, plus 1. All right, so now I take that and I factor by grouping. Here I have a common cosine, so I'm going to factor out that cosine. So I factor that, I'm getting cosine theta, but I also share 2, so 2 cosine theta. And what do I have left? I have cosine theta minus 1. In my second group, it only shares 1, but we have to show that we're factoring out that 1. And I have cosine theta minus 1. All right, guys, so now I rewrite this as that cosine theta minus 1 times 2 cosine theta plus 1, and that equals 0. Well, guys, let's take a look at that. What can I do from here? All right, so we're going back to how we solved it before. So let's take a look. I'm just going to push this up a little. Push this down so I can just get another sheet of paper. All right, guys. So what do I do from here? I set them both equivalent to 0. So I get cosine theta minus 1 equals 0, and 2 cosine theta plus 1 is equivalent to 0. And I solve. So here I'm getting cosine theta equals 1. Here I'm getting cosine theta equals negative 1, and then cosine theta equals negative 1/2. That's what I have here. So now if I take a look at this, I go to that unit circle, and when I go to my unit circle, I know when cosine is 1 and cosine is negative 1/2. So I'm looking at it, and remember, cosine's your x, so I'm looking for 1 and negative 1/2. And because it's on my unit circle, I don't have to worry about the calculator. And if I look at that unit circle, when is x equivalent to 1? X is equivalent to 1 at 0. When is x equivalent to negative 1/2? Well, I go around my unit circle, and it's equivalent at negative 2 pi over 3, and, positive 2 pi over 3, I don't know why I write negative. Positive 2 pi over 3 and 4 pi over 3. All right, guys? And that would be my 3 solutions to that problem. All right, so that double angle identity helped me out there. All right, let's take a look at another one. My second one I'm going to do is sine theta minus 2 sine of 2 theta equals 0. Now again, I see a double angle identity. Now this one's a little different because I have sine of 2 theta. I only have one sine double angle identity, so I have to use that one. So if I come up here and I look for sine of 2 theta, I'm looking right here. I see that sine of 2 theta is equivalent to 2 sine theta cosine theta. So that is the only thing that I can implement in here. I can input in here. So what I'm going to do, if I input that in, I'm going to get sine theta minus 2 sine theta cosine theta. But this still helps me in this problem, because if you look now, I have 2 terms. I have a binomial at 2 terms, and each term has a common sine theta. So I can now factor that sine theta out. So if I factor out that sine theta, I'm getting sine theta. If I factor out sine theta here, 1 is a factor of everything. I'm left with 1. Minus 2. I factor out this sine theta. I'm left with 2 cosine theta is equivalent to 0. And guys, I can solve this. I have 2 things. They're the products equivalent to 0. So what do? I set them both equivalent to 0. Get sine theta is 0, and I get 1 minus 2 cosine theta is equivalent to 0. And I can solve both of them. Sine is our y value. When is y 0? Well, y is 0. If I look at this, y is 0 at, in this case, we know it's at 0 and pi. Here, if I solve this, I'm getting negative 2 cosine theta equals negative 1, and cosine theta equals a positive 1/2. When is cosine positive 1/2? I look at that unit circle and I ask myself, when is x positive 1/2? And it's at pi over 3 and 5 pi over 3. So that means those 4 values are my solution to my trig equation. All right, guys? All right, I'm going to do 2 more for us, okay? And in the next one, what I'm going to do is utilize a different type of identity. So I want us to recall, we're going to look at our Pythagorean identities in the next 2, just so we remember them. All right, guys? So now if I take a look at this, my next problem I'm going to do is cosine squared theta equals sine squared theta plus 1. Now, if I look at that, guys, I remember my identity. I have a Pythagorean identity of sine squared plus cosine squared is equivalent to 1, and I can manipulate it. So right now, guys, I just have to pick one. I want to say I have a cosine squared and I have a sine squared. I want to rewrite this. I'm going to rewrite it in terms of sine, which is, you can do cosine, but we're just going to pick one. I'm going to rewrite it in terms of sine. And if I look at that little trig sheet that you have, that we know, I know that cosine squared theta is equivalent to 1 minus sine squared theta. And I know that from my Pythagorean identity little cheat sheet you guys have. The little blue sheet you have. So that means instead of cosine squared theta, I can plug in 1 minus sine squared theta. So here I have 1 minus sine squared theta equals sine squared theta plus 1. All right, guys, now I can solve this because I have the same trig term. I have a sine theta, and in this case, they're both squared, so I can actually combine like terms here. So if I look at this, I can add that sine squared theta to the other side to have 2 sine squared theta because they're like terms. And then I can subtract 1, and the 1s would cancel. So I'm getting 0 is equivalent to 2 sine squared theta. Well, if I take a look at that, that means if I divide by 2, 0 is equivalent to sine squared theta. And then that means sine theta would just be 0. Well, if I look at this, now I go to my unit circle. When is sine theta 0? When my y value is 0. When is y 0? It's 0 at 0 and pi. All right, guys? One more. I'm going to do one more today, and then you guys have an assignment of 4 problems to do. All right, guys, take a look at this. I have a cosecant squared theta and a cotangent. And I know, wait a minute, I need to write this all in terms of one of them. Well, if I think of cotangent and cosecant, again, I think of a Pythagorean identity. I know that cosecant squared, if you look at that little blue cheat sheet, you know that cosecant squared theta equals, you know it equals 1 plus cotangent squared theta. So remember, that cheat sheet is from, guys, that cheat sheet is from our trig identities, okay, guys? Just to make sure that it's from that trig identities. So if I look at that 1 plus cotangent squared, I'm going to plug that in for that cosecant squared, because then I have my equations all in terms of cotangent. It makes it easier for me to work with. So if I put this in, I get 1 plus cotangent squared theta minus 2 cotangent theta equals 0. Now, I'm just going to rewrite it because it's in quadratic form. And now I can say what adds to negative 2 and multiplies to a positive 1. And it's going to be negative 1 and 1. So I can factor this easily because my a value is 1. I get cotangent of theta minus 1 times cotangent of theta minus 1. I mean, they're the same thing. So I know it's cotangent of theta minus 1 has to be equal to 0. I only have to write it once if I want. And I know, therefore, cotangent of theta is 1. Now, this is where we have to remember. Cotangent of theta is 1. Cotangent is x over y. That means in order to have your cotangent be equivalent to 1, your x values have to be exactly, your x and y values have to be exactly the same. Look at that unit circle. When is your x and y values exactly the same? Well, in quadrant 1, I know that at pi over 4, x and y are both root 2 over 2. So therefore, root 2 over 2 over root 2 over 2 would simplify to 1. So theta would have to be, pi over 4 would have to be one solution. Continue around that unit circle. And when you get to quadrant 3, and you're at 5 pi over 4, you see that both x and y are negative root 2 over 2. So if you have a negative root 2 over 2 over a negative root 2 over 2, that again is going to simplify to 1. So these would be the 2 solutions to our trig function. The 2 times that cotangent is equivalent to 1. All right, guys, that's it for today. So you have 4 problems tonight. You're going to have to utilize your trig identities. Make sure you copy down your identities from the beginning of the lesson, the double angle identities. They're gonna have to be used in a couple of the problems. So please complete the problems, the assignment, and upload it on this assignment on Canvas. My office hours are gonna be a Google Meet. I will send an announcement with a link at the beginning of office hours. Please come ask questions if you have any, and I hope to see you there. Bye, guys.